Pretty good. Now we're all set. Okay. So just like gravitational field, electric field is can also be defined as a region where electric charge feels force. Now, unlike, however, gravitation, which is always attractive, this force can be attractive, depends on the type of charge, and it can also be repulsive. So, that's something you guys need to remember. Now, when you say a charge basically is just like we take it as a sphere. So there could be two types of charges. You might have done this already in O levels, which is it could be a positive charge or it could be a negative charge. Now, positive or negative charge does not mean this is just an electron. It means one charge is made up of many electrons and many protons. However, the difference is when it comes to the positive charge, the field basically goes through a single point like that, and then it basically is like that, goes through a single point, and in the positive charge the field is going out of it like that. So all arrows out. Okay. However, when it comes to the negative charge, the field is going into it like that, or directed towards a single point within it. Oh, please snap it like that. Okay, so it's going in. Now, if you notice that all the field is basically directed to a single point, and that is why we can actually call them as point charges. Point charges basically mean they're charges which seem to be originated from a single point, or all the fields are converged or emerged from a single point. Do you guys get what I'm saying?
Yes, sir.
Now, the question is that why are we making these lines like going, why are these lines going away from the center of a positive charge, and why it is converging to a single point in the negative charge? This basically has a convention that we follow. So electric field lines and their direction now depicts the direction of force on a unit positive charge. Now, writing this is very important. Unit positive, which means this is a convention that, let's suppose if I put a charge Q, which is positive, right where I've drawn right now, where would it basically feel the force? Away from the positive charge or towards it? So this one I'm talking about. It's basically going to feel a force because it's going to get repelled by this, so it's going to feel a force um, this way. This is why the direction of the field at this point is this way. Do you guys get it? And if I had put the positive charge anywhere on that field, so obviously it would have been attracted to it. That is why the direction of the field, that field is basically that goes into the negative charge. So what I'm saying is that wherever the force on the positive charge is, that is the direction of the field at that point. Get it? As simple as that. All right, please write this down and then I'm going to go forward. Okay. Dania, how are you? Huda, how are you? Laiba? Khatija?
Yes, sir.
Okay.
Good, sir.
Sameer and Zainab, how are you?
Fine, sir. How are you?
Fine, sir.
I'm okay, good. All right. Now, so keeping that in mind, then we need to understand, just like there was gravitational field strength. In this one, we will have electric field strength. Electric field strength is defined as force per unit positive charge. Now, writing positive charge, because this is a convention, is a key word. Please highlight this so you guys do not miss that out. Now, the symbol that we're going to use for electric field strength is E. The SI units for electric field strength would be newtons per coulomb, and it is a vector quantity, which means we're going to be very careful about its direction as well. By the definition itself, if you see, electric field strength is force per unit charge, like that. So this is the formula that we're gonna follow. Right. Just write here electric field strength. This would be force. This would be charge. Just like that. Okay. Now, field itself can be uniform and it can be non-uniform in electric fields, and we can actually create it very easily. So let's have a look. First of all, let's look at the uniform electric field strength and what it means. So uniform electric field strength, first of all, can only be created within two parallel plates. There is no other way you can create it. Now, parallel plates would. Let me just take it to the next page. It doesn't matter. Okay, let's keep it. It doesn't matter. Okay, so you have a plate like this, and then you have another plate like this. So one is connected to, let's suppose, one terminal. The other is connected to the negative terminal. So the field would be like that. Straight lines, equally spaced and parallel. At the corners, they bend a bit. I'm going to tell you why they do that in a bit. Just like that, right? So it always goes from positive to negative or higher potential, lower. Now, what are the features of this? Number one, it's all lines are straight. Number two, they are equally spaced. Number three, each point within the field has a constant value of electric field strength. So within the field, wherever you go, electric field strength is constant. That is why it is called uniform. Okay, just like that. Then copy this, please, and then we're gonna go forward. Okay. Now let's look at non-uniform field and try to understand how it differs. For example, you have a mass, a charge, which is positive, and then you have a plate like that, which is negative. So the field basically would be something like this. It will go from positive to negative, but then something interesting happens here. What you guys need to understand is while drawing the field will come out from the object at 90 degrees and it will enter back into the next object at 90 degrees as well, like that. Do you guys get my point?
Yes.
So if it's coming from this point, it will come out at 90 degrees and then it will curve back and enter here exactly at 90 degrees. This is the reason why the field would look like as if it's turning, but it's actually trying to enter and exit at 90 degrees at all times. Is it clear, everyone? Like that. Now, why is
Yes.
this non-uniform? Because if you look at this, you might see that lines are closer near this, but lines are further apart here. So which means that every point will have a different value of electric field strength. Same goes for another sort of diagram. Suppose there is a plate like this, and then there is a plate like this. Like that. So in this plate, let's suppose one is positive, one is negative. So it goes like this. 90 degrees out, 90 degrees in. 90 degrees out, 90 degrees in. And obviously, as the plates are going to go further apart, the strength of the field is also going to decrease because, you know, plates are not close together anymore, like that. So now we will learn two things. Number one, you write a note here. Lines enter and exit at 90 degrees from surface. Number two, strength of field is depicted by how close the lines are to each other. All right, you people. So naturally, in this strength, you will have higher strength of electric field strength. Here, you will have lower strength compared to the upper portion. So because it's closer like that. I hope that's clear. Abdul Rahman, everything is clear. Should I go forward now?
Yes.
Okay. So now, let's have a look at the next. So now this is a small derivation that we got to learn, and they might ask you this as well, which is the acceleration in an electric field. So write that, put a star on top because this is important. Now, we've just learned that electric field strength is given by force per unit charge. We also know, so let's write a small charge. We also know that force itself is equal to ma. It's pretty simple. We can write F equals to E times Q and F equals to ma. Because F and F will be equal, so we can put them together as EQ or equal EQ equals to ma. And then A will be equal to EQ over m, and that is the derivation of acceleration in electric field, like that. So E is the, again, electric field strength in this, Q is the charge, and m is the mass of charge. So that would be like, if it's an electron, what would be the mass of electron, proton, whatever it is. So it doesn't matter. A is acceleration, by the way. So please write this down as well. Now, few things from AS that I would like to point out, so that you guys do not forget about it. Just writing AS. So from AS, we need to learn that 1U is basically the unified atomic mass, and the value of 1U is 1.6 times 10 raised to power minus 27, 1.66. All right, so do remember that 1E is the elementary charge. I'm sure you
In
guys have
gram or in, for unified atomic mass, in gram or kilogram?
it's kg, sorry. And this is 1.6 times 10 raised to minus 19 coulombs. And mass of electron is mass of electron. We've used it in AS a lot of times, but if you have forgotten about it, time to remember it again. So this will be minus 31 kilograms. So these are already given, but you need to learn how to use that. So I'm just gonna revise it a bit so that we do not have problems right now. So for example, if they say that there is a helium nucleus which has a value of 4 2, okay, so automatically now it is assumed that that 4 is 4U and 2 is E, which means if you want to find the mass in kilograms, so that would be 4 times 1.66 times 10 raised to minus 27 kilograms. That would be that the nucleus of helium is going to be 6.64 times 10 raised to minus 27 kilograms, like that. And they, in any case, they require the charge in coulombs, then 2 times 1.6 times 10 raised to minus 19. That will be 3.2 times 10 raised to minus 19 coulombs. This is only for helium, by the way, so they can also give you other elements as well, but mostly either it is carbon or helium, so that's fine. Okay. Any questions, please let me know. Right. All right, the next. So this was AS portion that is required, but the next is that we also need to now start working. So we're going to analyze uniform electric field and how does it work. So I'm just gonna copy this. I don't want to draw it again. Okay, right here. Now see. Oh, by the way, I want to tell you why it curves. I forgot about it. I'm really sorry about that. Basically, it curves at the ends because it is like, it is like, let me just use a different color. So it's like this. So it needs to go out to 90 degrees from this. That's why. Do you guys get it? That's why it curves, because that's the point. Anyway, not important. Suppose that this distance between the plates, this distance, is given by D, which is equal to 8 centimeter. All right, this distance from one plate to another. Suppose that the value of potential is plus 20 volts here, and here it is negative 20 volts, right? So that's the potential, which basically gives us the idea that if I want to find the potential difference, which means if I connect a voltmeter right here, do you guys know what value will it give me? Any ideas? It's going to give me 40 volts gravitational potential. Oh, sorry, electric potential. So it's basically, potential is like a scalar quantity. You do bigger minus smaller. So 20 minus 20 will be 40. So this is what it is giving. So let me write it down as well. So the change in potential is always taken as, because it's scalar quantity, bigger value minus the smaller value. Always remember that. In scalar and vectors, we do final minus initial. Sorry, vectors, we do that. In scalars, bigger minus smaller. So it will be 20 positive minus 20. So this is going to give me positive 40 volts, like that. Or just 40, it doesn't matter if it's positive or negative. Anyway, now the next thing we're going to do is, and now starts the derivation that we need to look at. In AS, we have also learned that the potential is given by work done per unit charge. Remember, potential difference was given by this. Any
Yes.
recalling here? Okay. So in this one, you should understand that itself. Let me write the full form so you guys don't forget. It is work done per unit charge. Work done itself was force times the distance, right? Or displacement. You guys agree? If I write this as
Yes.
force times the distance over charge, because when a charge will move from this point, let's call this point, to this point, obviously it will cover this much of a distance. So that's what we're talking about here. Now, check this out. Can you recall anything that's equal to force over charge? Is that something you've just done?
Electric field.
Electric field strength. Yes, very good. So it means that we then will be equal to electric field strength times the distance. So electric field strength has another formula, which is potential difference over the distance between the plates. You get it? This formula is only for uniform fields. It cannot work on non-uniform. So you guys need to remember that. So just let me write it. This is potential difference. This is distance between plates, and this is field strength. Just like that. All right. Any questions, please let me know. From here, we also learn an interesting fact that the SI units of electric field strength are not only Newton per coulomb, but also volts per meter. So they are basically the same base units. So you can also work it out if you like to do some extra work. All right. I'm sure you don't want to do that. All right. Is it clear?
Yes.
Okay. So they can basically give you both the units. Don't get confused that, okay, where does these units come from? Now, what happens to the potential? We need to basically understand it through the graph as well. So let's draw a graph here. So here we have positive potential in volts. This is distance in meters, and this is basically negative potential in volts. Now see this. So what has truly happened here is that initially, when we start from this very point, you see the potential at the first plate was right here. Let's call this positive 20. You guys agree? And exactly in the middle, let me just do it with a different color. Exactly in the middle, right here, because the potential on both sides are like, one is positive, one is negative. Exactly in the middle, it should be 0. So it means exactly at 4 centimeter, the line would go to 0 and then continue going downwards till it reaches negative 20 volts, which is exactly at 8 centimeter mark. Do you guys get it?
Yes.
Okay. Now, a very interesting thing here emerges. It's basically a line that is straight and it's going from like positive to negative. Doesn't matter if it goes positive to negative. But if I at any point wants to take the gradient of this line, so the gradient of this line would be somewhat like, let's draw a triangle at any point like that. So the gradient of this line will be change in V over change in D. Can I say that? So the gradient of this line would be the change in V over change in D with a negative sign because it is a negative gradient. Everybody agrees to this?
Yes.
Yes.
Can you tell me from the screen what exactly is this?
Change in electric field strength.
This is electric field strength. Yes. So it means that the gradient of this graph is negative electric field strength. And why it is straight line? Because the gradient is constant and in uniform electric field, the electric field strength is also constant. Do you get it? Now, this is the reason most of the time the examiner, you will see that he is writing electric field strength, so also known as the negative potential gradient. It means that whatever is happening in potential graph would be the electric field strength would be the negative gradient of that. Understood?
Yes.
Yes, very good, very good. So now you understand what is the relationship between them. All right, you can draw this and write that. And if you have any question while you're doing this, please let me know. Yes, Zainab and Dark Legend and Dania, you guys understand everything?
Yes.
Okay.
Khadija Squares and Ryan and uh, Afan, Huda, Javeria, everything is clear?
Yep. Yeah.
Yes, sir.
Yes, sir.
Okay. All right. All right. So now that is pretty easy. Now let's go to a question and see what basically it requires us to do. So one by one, let's. I'm going to the next page now. So question and part I. It says, what will be the force on an electron when electric field strength is 4.5 times 10 raised to power 5 volts per meter. Now, please, as I'm doing this, you guys should be writing it down. Then, question number 2, how fast the electron be traveling if it accelerates from rest to a speed of v within 10 centimeter distance. All right. Then the third part would be, what would be the potential difference at 10 centimeter, assuming it travels in a uniform field. Okay, so this is the three questions that we got to. All right, so first one, any answers, please?
Sir, what's the charge on one electron?
1.6 times 10 raised to minus 19. You don't know that? That's very bad.
Sir, I got 7.2 into 10 to the power minus 14.
That is correct. That is correct, my friend. Very good. So, everybody, please try this. What formula did you use?
E is equals to F over Q.
E equals to F over Q. That is correct because we have electric field strength. We just need to find the force, which is good. So, let's do that. So, E equals to F over Q. F will be equal to electric field strength, which is 4.5 times 10 raised to 5, and charge on electron is 1.6 minus 19, 10 raised to power 19. So 7.2 times 10 raised to negative 14 should be your answer. All right, who could not understand this, please let me know. Now the real challenge is the next question. I'm expecting you guys to do that. Let's see. Now you guys need to calculate the speed if it starts from rest at the end of 10 centimeter linear distance. This is what they're asking.
I'm getting 1.26 times 10 raised to power 8 meter per second.
1.26 times 10 power 8. Okay. Anyone? Anybody else who has got the same? Okay. Nobody else? You guys are confused in this? Okay. Now, anytime it says that speed, so you got to basically learn about slew watt. The I think 10 into 10 raised to minus 2 meters. Then initial velocity is 0. Final is what we need to find. We do not have the acceleration given to us. We neither have the time. So it's okay because to find this, we can use 2as equals to v squared minus u squared. We know that acceleration electric field is eq over m. We've just learned this. So 2 times eq over m will be equal to v square and initial speed is 0, so like that. So it means v will be given by 2 eq over m. So this is what we're going to do, right? So now let's put in the values. So 2 times 4.5 times 10 raised to power 5 times charge on electron is 1.6 times 10 raised to minus 19 divided by the mass. So the mass of electron is 9.11 times 10 raised to minus 31 that I told you earlier. Oh, did I multiply S? Sorry, S is missing in this, right? EQS. S is 0.01. Sorry. And then
Wouldn't
you
it be
take the root.
0.1?
Oh, yeah, sorry. 1. All right. So then it should come out as 1.26 times 10 raised to power 8 meters per second. Any questions? Please let me know here. Okay. Fair enough. Then in the next part, it says, what would be the potential difference at 10 centimeter assuming that it travels in a uniform field? Is there a way to find potential difference?
E is equal to V over D.
V over D? Yeah, that's correct.
Yes.
E equals to V over D. Okay, are you sure about that? All right, yeah. Can you please find the answer?
4.5 times 10 raised to power 4.
V over D. So that would be basically the distance is 10 centimeter. Electric field strength is 4.5 times 10 raised to power 5 times 0.1. That would be how much? Sorry,
4.5 times 10 raised to power 4.
10 raised to 4 volts. Is it clear, everyone? Any questions here?
No.
Right. So that would be basically this. Now, up to this point, we've done with the uniform electric field. From tomorrow onwards, we will be going towards the Coulomb's law. And that would be it for today then. All right then. If you complete
Okay, sir. Allah Hafiz.